Now you may have wondered, well, if a star is a main sequence star, you're able to find the absolute magnitude of the star. All you have to do is find the color of the star relative to the temperature, and then find the corresponding luminosity on the vertical scale over here. But not all red stars are main sequence stars. There are a number of stars that are giants. Some of them are small giants, they call them subgiants. Some are regular giants, some are bright giants, some are supergiants. And of those, there's the very luminous supergiants and the less luminous supergiants. And you can see that there's a large difference in the luminosity of these stars, and they all are red. So how can you tell a red main sequence star from a giant red star, and which giant red star will it be? Because if you pick the wrong one, you're definitely going to pick the wrong luminosity for that star. Well, it turns out we were actually able to figure out for the number of subclasses of red giants, due to their spectral analysis, we can actually see subtle differences in the spectral lines that are more dominant in some giants than in others, depending upon their size. So we can actually identify which giant we're looking at, and identify that we're looking at a giant star rather than a main sequence star, so that we can find the correct luminosity. And so we've come up with a new subclass, a set of subclasses called the luminosity classes. And so the luminous supergiants are the class 1A, and the less luminous supergiants are class 1B. So they're both classed as the supergiant red giants. And so we have less and more luminous types of those. Then we have the next one where we have bright giants. They're not quite as big as the supergiants, but they're still giant red stars, so we call them the bright giants. Then we have the regular giants, which is luminosity class 3. And finally the subgiants, luminosity class 4, before we get to the main red sequence stars. And so that's how we've been able to identify those as well. Without going into details of how exactly we do that, that would be for another video, you can at least see that we can still find the luminosity of these red giants, and therefore for the red giants we can do the same thing as we do for the main sequence stars. We can find their absolute magnitude by simply looking at their color, then look at their luminosity class by looking at their spectral lines, determining which type of luminosity class it belongs to, and then from that go in here and read the actual luminosity of that, then compare that to the luminosity that we see them, that they appear as when we measure their luminosity, compare the two distances, and again find the distance, just like we did in the previous videos, to those stars. So we've got it pretty well covered. Now the red giants are a rare class indeed. Less than 1% of all the stars are red giant stars, so the vast majority are indeed the main sequence stars. But because the red giants are so interesting to study, and just because they're so bright, so they're easily found and seen, we still want to be able to determine the distance to those stars to understand them better as well. And that's how we do that. Welcome to our lecture online, and now we're going to take a look at another aspect of astronomy that really, and again, will enable us to figure out distances to things that are really far away beyond our galaxy. And that's something that Hubble took advantage of when he started studying astronomy, and he started doing research in astronomy. And when he began to realize something very, very profound in astronomy, it was based upon this concept right here. So let's understand this concept, which is the radial velocity of stars, and in that aspect, the radial velocity of anything, nebulas, galaxies, you name it. So how do we know how fast things are traveling through space? Well, stars are moving in all different directions, nebulas are moving in all different directions, galaxies are moving in all different directions, and so there always will be a component of that velocity that's either directed towards us or directed away from us, and that's called the radial velocity. For example, let's say that the Earth is over here, and there's a star, and let's say the star is moving in this direction right there, like that. Well, there will be what we call a radial component of that velocity, this way, and it'll be a perpendicular component of that velocity, which is in this direction like that. We can measure this velocity. We can measure velocities of galaxies or stars or whatever it may be in the linear direction away from us. That's called the radial direction. We cannot measure velocities perpendicular to our line of sight because there's no way for us to do that. But this we can measure. So this component right here is the component we're talking about right here. So if an object is moving towards us, we say the object is blue shifted. If an object is moving away from us, we say that the object is red shifted. What does that really mean? Well, first of all, let's find out how we can even tell that things are moving. Well, objects such as stars and galaxies are mostly made up of hydrogen. also a lot of helium, some other elements, but hydrogen is the most abundant element in the universe. And hydrogen has a very specific spectrum due to the electron jumps from lower orbits to higher orbits and back to lower orbits. Hydrogen will absorb and emit photons of exact specific wavelengths. And for specific jumps where the electrons jump back down from the third level down to the second level, from the fourth level down to the second level, and from the fifth level down to the second level, it will emit a photon of a very specific wavelength in the visible spectrum. One wavelength will have one photon will have a wavelength of 656.3 nanometers to be exact, and that will give off red light. We have another one at 486 nanometers that will give off bluish green light, and one that will emit at 434 nanometers, which is purplish light, like violet light. Now, objects that move towards us or move away from us, those wavelengths will be shifted. If an object is moving away from us, it will be shifted to a higher frequency, therefore a lower wavelength. And so here you can see that when it's blue shifted, the photons will be shifted towards the right. That's a lower wavelength, so instead of maybe 656 nanometers, the wavelength will now be 654 nanometers. Shorter wavelength shifted towards the blue. Objects that are moving away from us, those frequencies will be shifted towards the longer wavelengths, and you can see that, for example, instead of 656 nanometers, we can measure that red light at 658 nanometers. Those are just examples depending upon how fast they may be moving. So how we can then get the velocity from that is simply to throw it into this equation right here. The velocity in a radial direction of an object, either moving towards us or moving away from us, is equal to the speed of light times the ratio of the amount of the shift of the wavelength divided by the original wavelength. So here, let's say this would be the original wavelength. And let's say that we go from 656 to 658. So the delta shift is equal to 658 nanometers minus 656 nanometers, which is 2 nanometers. So the shift is 2 nanometers, and the original was 656. So when we take that ratio right here, we get 0.00305. If we multiply this times the speed of light, we should be able to get the speed of that star. So we multiply this times 300,000, and we get 915. So V equals 915 kilometers per second, which would mean that star is moving towards us. Oh, no, is it moving towards us? Let's see here. No, the wavelengths are getting longer. That means it's moving away from us. So the object is moving away from us at 915 kilometers per second. So we call that redshifted. Sometimes instead of writing the equation like this, they will write the equation like this. The velocity is equal to the speed of light times the z factor. The z is called the redshift because most objects in the universe are actually moving away from us. We then use that z as a redshift term. So we simply take this as the fraction between how much the wavelength has shifted divided by the total, divided by the original wavelength. And it doesn't matter which one we take. We can take this one or any wavelength of any emission and see how much it had shifted and just come up with that ratio. That ratio will be the same no matter which one we take. The deltas will change, of course. For smaller original wavelengths, the delta will be smaller, but the ratio will always be the same. So they call that the redshift. And so the velocity is equal to the redshift times the speed of light. And so again, if you do it like this, you get the same number of 915 kilometers per second. If it's blue shifted and it's moving towards us, again, you can then call it a blue shift, plug in the number. You may want to call it a negative because then the number is getting smaller, which means then it's moving towards us rather than away from us, if that makes it clearer for you. But that is a very important thing. Notice we are able to figure out the speed at which things are traveling towards us or away from us for any object in the universe, even for galaxies. And that's going to be the key to figure out how far it is to these galaxies. So knowing this, having learned this, comparing that to the HR diagram, and now comparing it to some other means of finding distances to stars and distances to galaxies, we're going to find incredible, clever ways of finding distances to faraway objects like galaxies in the universe, and that will uncover a very new chapter in astronomy for us. So if you're interested, stay tuned. I'll show you how we did that. Welcome to our lecture online, and now we're going to take a look at one of those amazing discoveries in astronomy made by Hubble. And there's a reason why we call the Hubble Space Telescope Hubble Space Telescope. It was named after the famous astronomer Hubble for a very special reason. And the primary reason why we spent billions of dollars building and sending the Hubble Space Telescope up in space had a lot to do with Hubble's discovery and the relationship between them, and you'll see in a while why that is so. So what did we discover, and what did Hubble discover from that? Well, in the previous video I showed you how we were actually able to find the radial velocity of objects moving towards us or moving away from us. And when we started utilizing that equation and we started looking at stars, we saw that stars were moving in all directions and their radial velocity could be measured. But then we started looking at nebulas and things that looked like these strange nebulas, these glowing things way out there. Well, we used to think that these things were actually inside our own galaxy. So here's the picture of our Milky Way galaxy, here's the sun, here's my telescope, we're looking out. And we thought that these nebulas we were looking at were actually part of our Milky Way galaxy. We used to think that this was the universe right here. But then we started realizing, no, those things are actually way outside of our galaxy. Perhaps they're just like our own galaxy, just multiple copies of them. And when we started looking at the spectrum of those things, we started realizing that their spectrum had shifted to the red. They had been redshifted, meaning that they were moving away from us independent of the velocity of our own Milky Way galaxy. And then Hubble made the tremendous discovery that he began to realize that the galaxies that are farther away from us were moving away from us faster than the galaxies that were closer by. That in itself was a tremendous discovery. So what he did was he started looking at these galaxies very carefully. He started measuring their redshift. He then calculated their velocities, and then he tried to estimate how far these galaxies were. Now here was the big problem again. How far are things in the universe? Remember, that's the #1 problem in astronomy, and he had no good way of figuring out how far it was to the galaxies. But it did make the general assumption that if the galaxies were farther away, they would look smaller, and if the galaxies were closer by, they would look bigger. Of course, that's only true if all the galaxies were the same size, which by no means is true. But in general, the farther you look, the smaller the galaxy should appear on average. And so he felt that that was a fairly safe assumption to make, and he began to draw his diagram. So just like Hertzsprung and Russell drew the HR diagram, here Hubble drew the Hubble diagram. And so what he began to do was, on the vertical axis, put down the velocity of these galaxies, and on the horizontal axis, the estimated distance. And when he started doing that, he started getting points that looked like this. And he began to see that there seemed to be a linear relationship between the velocity and the distance. That was that great discovery. He saw that linear relationship. And then when he connected those with the best fit line, he ended up with something like that. Of course, it should come out to the origin right there. Now let me redraw this because I don't want to misdraw that. So this should have gone right straight to the origin. There's my distance axis. There's my velocity axis. And this looks very much like what you might have seen in algebra before, the y equals mx plus b equation, where m was the slope of the line, y was the vertical axis, x was the horizontal axis. So in the same way, he built up an equation where the vertical axis was velocity. The slope, we call that the Hubble constant, h sub naught, known as the Hubble constant. And then, of course, on the horizontal axis, we have distance. Now, understand the tremendous advantage behind getting this equation correct. Because then again, if this was a correct slope, you could then go look at a galaxy, measure its velocity, then find the velocity on the diagram right here and say, okay, it's going this fast, so therefore it must be this far away. And so now we had a new way of having a way to find the distance to galaxies. Of course, this is only a good way to find it if this overall diagram was correct, if h was correct. And of course, this was all built on the premise that he could figure out how far galaxies were simply by how big they appeared. And he was actually very far off. So what it came down to, if you solve this for h, you have h sub naught, the Hubble constant, is equal to the velocity divided by the distance. And his first estimate was that this was around 500 kilometers per second for every 1 megaparsec. Now, mega, of course, is million, so megaparsec is a million parsec, or 3.26 million light years. So he felt that if a galaxy was 1 megaparsec away, it was moving away from us at 500 kilometers per second. If something was 2 megaparsecs away, it would be moving away from us at 1,000 kilometers per second. 3 megaparsecs, it would be moving away from us at 1,500 kilometers per second, and so forth. So that would be fantastic. Then you can go and say, okay, if it's moving this fast, it must be that far away. Unfortunately, he was way off by his estimate. It was not 500 kilometers per second per megaparsec. We've been trying to measure that Hubble constant accurately for the last 100 years. So since he came up with it in the 19 teens, it's been 100 years. We're still trying to measure that constant very, very accurately because it has a tremendous impact in our knowledge and understanding of the universe. Today, the accepted number is more like 73 kilometers per second per megaparsec. Knowing how far off he was, kind of by a factor of 7, you can see how difficult it was back then for him to figure out the distance to these galaxies. And that was the main reason why he made such a large error in those estimations. However, the whole premise is correct. The fact that there is a linear relationship between the velocities of galaxies and their distances is still correct today, and that is one of the primary ways in which we can figure out the size of the universe and how fast things are moving. Well, not how fast, but how far galaxies are in the universe. This is the primary way. All we have to do is get a more accurate value for this. And guess what? The biggest reason why we send the Hubble Space Telescope up there in space is to find a way to get a better accurate value for this Hubble constant. And one more thing, why is Hubble constant so important as well? Is because the inverse of that constant, which is amazing when you think about it, 1 over h sub naught, is now considered to be the age of the universe. So not only does it allow us to figure out how far things are in the universe, it also is able to let us figure out how old our universe is. All predicated on this concept that the farther galaxies are, the faster they move away from us, the closer they are, the slower they move, and the velocity change is actually a linear function of distance. Amazing thing. If you're interested in this, come back for the next video, and we'll talk a little bit more about how Hubble constant can determine the age of the universe. Welcome to that lecture online, and here we have one of the great mysteries of the universe solved. Not only do we have an answer to the age of the universe, which is the inverse of Hubble constant, and I'll show you in just a moment why that is so, but there's another incredible aspect of the understanding of Hubble constant and what it implies. So let me try to explain to you with what I have on the board here. These are supposed to be galaxies. I know they look more like flying saucers, but they're actually supposed to be galaxies. And this is our galaxy, the Milky Way galaxy. So this is our home. That's where we live. And let's just, for the sake of argument, assume that there's galaxies all around us. Of course, that's not just an argument, that's a fact, of course, but in a very specific way, and of course, that's not going to be exactly this way. But let's say that there's another galaxy, 1 megaparsecs on one side of us, another galaxy, 1 megaparsec to the right. Let's say we have a second galaxy that's 2 megaparsecs away, and a third galaxy that's 3 megaparsecs away. So even though Hubble initially didn't get his own Hubble constant correct, because that took a lot of work from a lot of people to get that more precise, we today know that the Hubble constant, and let me write it down, the accepted value for the Hubble constant is now around 73 kilometers per second per megaparsec. What that means is that if an object, like a galaxy, is 1 megaparsec away from us, it will be moving away from us at 73 kilometers per second. That also means that if a galaxy, and let me write it down here, so this one is moving away from us at 73 kilometers per second, but it also means that a galaxy that's 2 megaparsecs away from us is moving twice as fast away from us. That would be 146 kilometers per second. And a third galaxy that's 3 megaparsecs away from us would be moving away at 3 times that speed, which would be 219 kilometers per second. And so forth. And then, of course, the galaxy that's 4 megaparsecs away would be moving at 4 times that speed, and 5, and so forth, and so on. This is very interesting. Wow. All galaxies are moving away from us proportional to the distance between the galaxies. So it's not really as if the galaxies are moving. It's more like space itself is expanding. And that was the automatic conclusion that people had to draw from this, that if everything is expanding so uniformly, simply proportional to the distance between galaxies, that means that it's really space that's expanding, and it's almost like as if the galaxies are stuck in space, and space is expanding, and the galaxies are simply moving with space. And in essence, that's exactly what's happening. It's not like the galaxies are flying away from each other. It's simply that they're stuck in space, and space itself is expanding, and the galaxies are simply going along for a ride. It's almost like the universe, space, is like a big spider web, and then the galaxies are like flies in the spider web. And if you were to take the spider web on all ends and pull on and expand it so that the web itself is expanding, then the flies stuck in the web would simply be moving away from each other. And two flies that are twice as far away from each other would be moving from one another twice as fast. And two flies that are 3 times as far away from each other would be moving from each other 3 times as fast, and so forth. It's almost like space is the spider web and the galaxies are the flies. Some people don't like that analogy. Sometimes they use the analogy of a loaf of raisin bread. When you first make a loaf of dough and you put yeast in it, you put raisins in it, and the bread begins to rise, then the raisins begin to move away from each other, proportional to the distance between them. If there's twice as much dough, or twice as much dough between the raisins, then they would be moving twice as fast. 3 times as much dough, they would be moving 3 times as fast as the raisin loaf is rising with the yeast. And so the raisins are the galaxies, and the dough is space. Space is something that's actually expanding, and everything in the universe is expanding along with it at the appropriate rate, which is amazing. Some people will say, well, are we then in the middle of the universe since everything is moving away from us? And not really, because what if there's somebody living on this galaxy right here? Some other being, not necessarily a human being, but some other being, and they're looking around themselves and they say, wow, look at this. This galaxy is moving away from us at 73 kilometers per second. And this galaxy is moving away from us at 146 kilometers per second. And this galaxy is moving away from us at 73 kilometers per second. And this galaxy is moving away from us at 146, and so forth. So no matter where you are in the universe, everything will be moving away from you at the exact same way, no matter what galaxy you may happen to live on. So the whole galaxy is expanding everywhere in the exact same way, and therefore Hubble constant is the constant that determines the speed at which the universe is expanding. Now, how does the inverse of the Hubble constant give us the age of the universe? Let me show you that. So since the Hubble constant is 73 kilometers per second per megaparsec, taking the inverse would be 1 over that, which would be 1 megaparsec per 73 kilometers per second. And 1 megaparsec in light years is 3.26 million light years. And then, of course, a light year is the distance light travels in a year. So instead of a light year, we can replace it by the distance covered in a year, which is the speed of light, times the time in seconds, because this is 300,000 kilometers per second, and 1 year is this many seconds, 86,400 seconds per day, and 365 and a quarter days per year. Now with a calculator, we should be able to figure out how many seconds that is. So that would then be the age of the universe. So 3.26 e to the 6th divided by 73 times 300,000 times 86,400 and times 365.25 equals, and we get the age of the universe, according to Hubble constant, is 4.23 times 10 to the 17th seconds. Wow. Now, how many years is that? Well, now we have to reverse course. So if we then divide that by the number of days, so divide by 365.25 days and divide by 86,400 seconds in a day, we now come out to, this is equal to 13,400,000,000. So 13,400,000,000 years, or 13.4 billion years. Amazing. Now, we haven't known the accuracy of the Hubble constant for that long. It wasn't that long ago that people thought that the Hubble constant was maybe 100 kilometers per second per 1 megaparsec. In that case, the universe would be would be only 10 billion years. And then there was a time when we thought that was only 50 kilometers per second. In that case, the universe would be 20 billion years old. So you can see over time, as we're getting closer and closer to the good, accurate value of the constant, we're getting a better and better reading of how old our universe is. Now, it turns out, back in the late 1990s, they discovered something else very strange. They discovered that the expansion of the universe was not constant. And I'll show you in a later video how they discovered that and how they adjusted for that. So the actual true age of the universe, well, true age, as best as we can calculate it with our refined calculations, is that the age is more like about 13.84 billion, because the universe expansion is actually accelerating. So that means it was going slower in the past and it's going faster now. It means slower in the past, meaning the universe was expanding more slowly, and therefore it took longer to get where we are today. Now, here's another way of looking at it. Why is 1 over Hubble constant equal to the age of the universe? Well, imagine this. If two galaxies are 1 megaparsec apart and they're currently moving away from each other at 73 kilometers per second, how long would it take for the galaxy, if we assume that this galaxy was right next to our galaxy at the beginning of the universe, how long it would take for it to be at this distance right here? And so that's what we do. We take the distance divided by the time, and we get the time it takes for this galaxy to have traveled this distance away from this galaxy. Now you can say, well, what about the second galaxy? It's twice as far away, but it's also moving twice as fast. So that means that in the same amount of time, this galaxy will have moved from right being next to this one all the way to twice that distance. Wow, what about the third one? Well, this galaxy is 3 times as far away, but it's also moving 3 times as fast. So for it also, in the same amount of time, it would now have traveled this distance, which means if everything in the universe is expanding at the same rate as a function of distance of space between each other, then you can see how the whole universe is expanded to where it is today, and that means that the whole universe at the beginning of the universe would have been all in the same location, close together. So that's why 1 over the Hubble constant equals the age of the universe, because 13.8 billion years ago, all this matter, all these galaxies, all these stars, all the hydrogen and helium makes up the universe should have been in the very same location close together, and it's been expanding ever since. Wow, what a discovery. All because of the understanding of how we can calculate radial velocities, and then Hubble, who then figured out that the expansion of the universe is evident in how the galaxies are moving up away from each other, proportional to the distance between them. What a discovery, and that's the result of it. Welcome to our lecture online, and now we're going to take another look at how they determined the accuracy of the Hubble constant. Remember, Hubble was way off, probably by a factor of 7 or 8, where he thought that the Hubble constant was in the 500 range, 500, 550 kilometers per second per megaparsec, which we now know today is completely wrong, of course. But the concept was there, that there was this linear relationship between the recessional velocities of galaxies and the distance from, to those galaxies. So if the galaxy was twice as far away, it was moving twice as fast. 3 times as far away, it was moving 3 times as fast. But how do we find an independent way of measuring the distance to those galaxies? Well, back in 1977, Brent Tooley and Richard Fisher came up with this ingenious concept where they had studied the spin flip radiation coming from galaxies. Now, what does a spin flip mean? Well, it turns out that electrons have various quantum mechanics states in which they can exist inside the atom. And one of those quantum mechanics states is what we call the spin flip, where an electron can basically be what we call spin up or spin down. It's a quantum mechanics state in relation to the electromagnetic fields inside the atoms that cause electrons to be oriented one way or the other way in terms of the angular momentum and in terms of the electrical forces due to the attractive and repulsive forces due to the charges. And so we can then measure that radiation. It turns out that the photons emitted when the spin flip like that occurs, remember that there's the possibility of having 2 electrons in a single orbital, and if the 2 electrons are in the same direction, then they have what we would call a less stable state than if they're in opposite directions. So the electrons can spin like that, and when they do, they release a certain amount of energy equivalent to a 21 centimeter long wavelength of radiation, which is kind of between radio radiation and microwave radiation. that radiation is able to make it through the dust and nebulas inside galaxies, so it's an easily measured radiation. And what they found was that the larger the galaxy, the more luminous the galaxies are, the more that line is spread wide. So for large galaxies, we have the line that spreads out very thick, and so we have a very wide spreading of that line. And for smaller galaxies that are less luminous, the line is much narrower. Of course, those things are hard to measure, but nevertheless, they realized that there was this linear relationship. And because of that, they were able to then determine the distance to galaxies in an independent fashion. And they utilized that to come up with a more accurate form of the Hubble constant, the Hubble equation here. And when they went through all their calculations, they found that in their estimation, the Hubble constant was somewhere between between 80 to 100 kilometers per second per megaparsec. Now notice that when Hubble came up with his constant, it was around 500 or 550. With Thule and Fisher, we were able to narrow that down to between 80 and 100. Still not correct, because today we know that it's much closer to 73 than it is to those numbers. But it was a nice improvement, an independent way of trying to measure the Hubble constant accurately. Simply that simple observation saying, wow, look at that. For large galaxies with a lot of luminosity, this line is very much spread out. For small galaxies, it's much more confined to a narrow area. And when they found that linear relationship, they were able to turn that into a more accurate value for the distance of galaxies. Very nice, but wasn't good enough yet, so we had to come up with even better independent ways. Welcome to Electron Line, and now we're going to take a look at what we call Type 1a supernovas and their relationship to the Hubble constant. Remember, the whole idea behind the Hubble constant was that we had to find the value of that Hubble constant accurately so we can use it to find the distance to anything in the universe. And again, if we want to take a quick review here, the Hubble constant was simply a linear relationship between the recessional velocity of galaxies and the distance of those galaxies. And Hubble found that first back in the 19-teens, over 100 years ago. He figured out that relationship, and he came up with the Hubble constant, the relationship, which he called Hubble constant, but the value that he came up with was really a wrong value. And the reason, here it is, that's the value, pretty well what he came up with, about 500 kilometers per second per megaparsec, which was off by a factor of 7 or 8. It's much closer today, as we know, to about 73 kilometers per second per megaparsec. But it all came down to finding a way to find the distance to galaxies in an independent fashion. So one way in which we could do that is by studying Type 1a supernova explosions. They last about 30 days. It's when a white dwarf star exceeds its Chandrasekhar limit, exceeds 1.4 times the mass of the sun. When it does, the star simply explodes. And when it does, it has a maximum brightness of -19. That's the absolute brightness. Now notice the explosion lasts for about 30 days. It takes several days to reach up to its maximum value. If we measure it correctly and we watch it correctly, we can find out when that happens. We then try to measure the apparent brightness, and we compare the two things. So let's say we have an apparent brightness of about +10. So that means we were looking at it with a telescope, we kept measuring it and measuring it. We reached its maximum value, we tried to measure the brightness of that galaxy. We then know, of course, that the absolute brightness, the real brightness, is -19. And then, of course, we simply take the difference. So what that means is that if the actual explosion happened at a distance of 10 parsec, it would have a brightness of -19. But instead, when we measure it, since it's so far away, it only had a brightness of +10. That's a difference of, let's see here, delta m. So the delta m here would be about 29. So then to find the difference in intensity, we take 2.512, raise it to the 29 power. So this is equal to 2.512 raised to the 29 power. And when we do that, let's see what we get. So 2.512 raised to 2.512 raised to the 29 power. And we get 3.99 times 10 to the 11th. Big number. All right, so that would be the difference in intensity, the difference in luminosity, to where it's actually occurring to where what it would be if it was only 10 parsecs away. So therefore, to find out where it actually occurred, the distance, we take the distance 10 parsec and multiply times the square root of the difference in intensity, because remember, the intensity is proportional to 1 over the distance squared. So therefore, the distance to the galaxy, which is where the type 1a supernova occurred, is 10 parsecs times the square root of 3.99 times 10 to the 11th. So let's take the square root of that. So that gives us d equals 10 parsecs times 6.31 times 10 to the 5th. That's 631,000 times 10. So that means that d equals about 6.31 megaparsecs, which is about 20 million light years. 20 mega light years. So that's how we do that. We find a galaxy, we observe a supernova explosion, we then measure the recessional velocity, then we find its actual distance, and then we use that as a dot on the plot right there. So we measure the recessional velocity, we measure the distance using this technique, and then we get a dot on the curve like that. And so we find more dots, and then we connect it with a straight line. We do exactly the same as what Hubble did. Instead, this time, we use the supernova explosions to find the distance to these galaxies. And when we used that technique, we found that Hubble constant was equal to somewhere between 40 to 65 kilometers per second per megaparsec, which was actually at the low end of a lot of other attempts that we had to find the distance, to find the Hubble constant. If that was a true value, that would mean that the universe was more like about 20 billion years old. And for a while, that was the accepted value of the age of the universe, that it was closer to 20 billion, rather to what we now know is close to 14 billion years, or slightly less than 14 billion years. So again, it was a very good method. We still use this method today, but today we can find more refined values for these measurements, and therefore our current value for the Hubble constant based upon this method is coming much closer to the value 65 rather than the range of 40 to 65. So again, these techniques are all good techniques, but it took decades and decades of hard work and hard science to try and come up with that exact value of Hubble constant. So another way to relate Hubble constant to distances of galaxies using the type 1a supernovas. Welcome to Lecture Online, and now we're going to take a look at variable stars and how we can use them to figure out distances to other galaxies or other parts of our galaxy. And the first type of variable star is what we call the RR Lyra star. We first found one of those in the constellation Lyra, and therefore we now call all these types of variable stars RR Lyra variables. Now it turns out that RR Lyra variables are really red giants who are near the end of their life cycle, and when red giants reach the end of their life cycle, they begin to pulsate, they begin to vary in brightness over certain periods, and those periods are fairly constant. So for the smaller red giants, the period is somewhere between 7 and 24 hours. So every 12, 13, 20, 24 hours, the luminosity or the brightness of the star increases and decreases over these very regular intervals. We've been able to measure independently that the luminosity of these stars is about 100 times the luminosity of the sun, which gives them a magnitude of about 0, an absolute magnitude. Further analysis shows that the absolute magnitude averages more like 0.75, so they're not quite 100 times as bright as the sun. But what's nice about it is they are fairly bright, and they have these very regular intervals of pulsation that is easily measured over a single observation of a nighttime. And so from that, we can then realize that if we see one of those RR Lyra variables in a nearby galaxy up to a distance of 300,000 light years, we can actually find the distance to those galaxies. Unfortunately, 300,000 light years isn't very much, so it can only be used for the galaxies that are very nearby, the small satellite galaxies of the Milky Way galaxy. We can't really see anything beyond that. So they're a limited value, but nevertheless a nice independent way of finding distances of galaxies. What we had to find was the variable stars of the variable red giants that are larger, so easier seen at a much greater distance, and yes, there is such a variable. It's called the Cepheid variable, and that became the key to trying again to establish an independent way of finding distances to the nearby galaxies, so we can check and improve upon the actual Hubble constant. So in the next video, we're going to take a look at Cepheid variables, which was really, again, one of those major breakthroughs in determining distances independently from the Hubble constant, and therefore be able to verify how correct Hubble constant is. So stay tuned for that one, and you'll see what Cepheid variables are like. Welcome to Lecture Online, and now the key to finding the correct value for the Hubble constant. And it's not so much that it's the correct value, because we never really will find the correct value, but we want to get as close as possible with as small as possible of an experimental error. And the key to doing that was the Cepheid variables, because Cepheid variables, just like the Lyra variables, have very consistent periodic changes in the luminosity of the star. And again, these are red giants, but larger red giants than the Lyra stars, and they pulsate at periods anywhere from 1 to 100 days. But what's so great about Cepheid variables is that their luminosity is linearly proportional to the periodicity of their periods. For Cepheid variables that have a variable like a pulse that vary in luminosity, that's a better way to say it, that vary in luminosity on average like 1 day or more, they have a luminosity, or they have an absolute magnitude of about -2. But Cepheid variables that vary over a period of 100 days have an absolute magnitude of -8. And the linearity between those two is very, very accurate. So therefore, all we have to do is find the Cepheid variable, watch the periodicity, so they become brighter and dimmer and brighter and dimmer. So the period is anywhere from 1 to 100 days. And so what we do is we find one, we measure the periodicity. Once we find the periodicity, we then go over here and find the absolute magnitude. Once we find the absolute magnitude, we then have to measure the apparent magnitude, and by using those two values, we can actually find the distance to that Cepheid variable fairly accurately. And if that Cepheid variable exists in another galaxy, we then know the distance to that galaxy, and then we can look at its recessional velocity, and from that figure out the Hubble constant. So again, what we're going to do, we're going to measure a whole bunch of Cepheid variables. We're going to therefore find the distance to the galaxies that they're in. We're going to note the recessional velocity of these galaxies. So on the vertical axis we have velocity, on the horizontal axis we have distance. We then connect those with the best fit line, and then we measure the slope of that line, and the slope of the line will be equal to the Hubble constant. By doing that, the value that we got for the Hubble constant ended up being somewhere between 60 to 80 kilometers per second per megaparsec. With again, the current accepted value falls right in between those two values, so we began to become very accurate in establishing the Hubble constant using Cepheid variables. There's only one problem. A Cepheid variable still is a single star, and to measure the intensity or the luminosity of a single star that are millions of light years away in another galaxy is very difficult to do, especially with earthbound telescopes. The best earthbound telescopes at the time could measure objects with a magnitude of about +22. So how far away can we see an object that has a magnitude of +22? Well, let's see here. If the absolute magnitude is somewhere between -2 and -8, how much brighter is that? Okay, so again, we're going to try and find the distance at which we can see an object that's at -2 and an object that's -8. So the way we do that is we find the apparent magnitude, which of course, this becomes the apparent magnitude. We're going to look for one as far away as possible. So the apparent magnitude will be +22, and the absolute magnitude will be, let's start with the dimmest of the Cepheid variables, a -2, so that the delta M is equal to 24. So the next thing we do is we find the difference in the intensity, which is equal to 2.512 raised to the delta M power, which is equal to 2.512 raised to the 24 power, which is, and with a calculator, let's find out what that is equal to. That's 2.512 raised to the 24 power. That's equal to, let's see here, that's equal to 3.99 times 10 to the 9th. Of course, then to find the distance to the farthest distance that we can see that with a telescope like this, that means the distance is equal to 10 parsecs times the square root of the difference in the intensity. So it's equal to 10 parsecs times the square root of 3.99 times 10 to the 9th. So let's take the square root of that, times 10 parsecs. And let's see here, that would be equal to, 0.6 megaparsecs, which is about 2 million light years, 2 mega light years. That's not very far. So the dim Cepheid variables can only be seen at the maximum distance of about 2 million light years. Well, what about the very bright Cepheid variables, the one that have a magnitude of -8? So let me use a different color for that. Let me try green. All right, so then at that point we have, and I'm trying to get the cap of my pen, there we go. So instead of a magnitude of -2, we now have a magnitude of -8, which is a difference of 30. So that means we're going to change this to a 30, and so we're now going to get a new value for the difference in intensities between seeing it at 10 parsecs and seeing it where it actually is. So 2.512 raised to the 30th power, that's equal to 1.00 times 10 to the 12th. Then we plug that value in here. And so now we get 1.00 times 10 to the 12th. We take the square root of that, multiply times 10, and what do we get? We get that is equal to 10 megaparsec, 10 million parsec, which is about 31.6 million light years. So with the biggest telescopes in the world, we can see a single Cepheid variable that has an absolute magnitude of -8, so the type that have periodicities of 100 days, in galaxies 30 million light years away, which is a good thing because in that respect we can go look at those galaxies far away, hope that we see a Cepheid variable, so we go searching. If we see variable stars, we'll measure the periodicity. Only the very brightest ones can be seen. We measure the length of the periodicity. Let's say it's one that has a periodicity of 90 days. We come over here, we see the absolute magnitude. We then calculate the apparent luminosity. So we compare the apparent luminosity to the actual luminosity, the actual magnitude of the star. We compared the two and then tried to figure out the distance to that galaxy. And so we did that for a number of galaxies, and we came up with this value right here, from 60 to 80 kilometers per second. But yet, we were not satisfied. That was just not good enough because we still couldn't narrow it down any better than that. What's the next step? We need a better telescope. One that can see things that have dimmer magnitudes than +22. And then we realized that an earthbound telescope could not accomplish that. Hence, let's put a telescope up in space. And that's why the idea came up to build the Hubble Space Telescope. The primary purpose for the Hubble Space Telescope was to go look for, you guessed it, Cepheid variables. But with the Hubble Space Telescope, we could see stars not just dim to +22, but dim to +30. That's another eight magnitudes dimmer, which means we could see Cepheid variables out to a distance of almost 100 million light years for the very bright ones. And that's what we wanted to do. So we built a Hubble Space Telescope, put it up in space. Yes, we took beautiful pictures with the Hubble Space Telescope, but we also were able to measure the Cepheid variables to even a greater distance. And by then, our better estimate then went down to 73 kilometers per second per megaparsec. And we owe this ability to come up with such an accurate value for the Hubble constant by using the Hubble Space Telescope to hunt for Cepheid variables in galaxies 50 to 100 million light years away. So we took the measurement of a number of these Cepheid variables over a wide range of galaxies, and we end up coming up with a much better value for the Hubble constant. And that's how we did that. Welcome to iLecture And now let's talk about the Hubble Space Telescope and Cepheid variables. Remember that Cepheid variables were these variable stars that had periodicities of 1 to 100 days. And we also discovered that the periodicity had a linear relationship with their luminosity or their magnitude. So Cepheid variables vary from -2 to -8 as their absolute magnitude. That's pretty bright because compared to the sun, our sun is like almost a +5. So these are variable stars. They're stars that are like as much as 10,000 or more times as bright as the sun. And their luminosity, or their brightness, depended upon the number of days it took for their periodicity to change, because they become brighter and dimmer and brighter and dimmer and so forth, anywhere between 1 and 100 days. So all we had to do was measure the periodicity of the Cepheid variable, put it on the graph, and read off how bright they were. And then we tried to measure their brightness as the way it appeared, their apparent brightness. We compared it to their absolute brightness, and from that we should be able to figure out the distance to the Cepheid variables. Now, if the Cepheid variables are embedded in a galaxy, and we take a number of readings over a number of Cepheid variables and average it all out, that would give us a fairly accurate reading to the distance of that galaxy. The next thing we do is we measure the recessional velocity of the galaxy. How do we do that? Well, the velocity is equal to the speed of light times the change in the wavelength caused by this recessional velocity divided by the original wavelength if the galaxy was not changing, and we do that for a specific spectroscopic value of, for example, hydrogen or some other gas that we know the exact value of, and from that we can find the exact velocity. We then put that on the Hubble curve. For example, we have the velocity on the vertical axis, we have the distance on the horizontal axis. So we use the distance from the Cepheid variables and the recessional velocity from our calculations. We start putting on these different values, and then we connect them all like that, and now we have a nice slope that represents the Hubble constant. Well, we did that for about 800 Cepheid variables in as many as 18 different galaxies as far away as 65 million light years. Remember, without the Hubble constant, we couldn't measure Cepheid variables that far away. One good example is M100, a very large galaxy in the Virgo cluster, 56 million light years away. We're able to detect 19 Cepheid variables in that one galaxy alone, giving us a very accurate reading as to the distance of that galaxy, and then also by measuring the velocity very accurately, we're able to come up with a very nice curve for the Hubble constant. In the end, with all this work with the Hubble telescope, the Hubble constant came out to be about 73 kilometers per second per megaparsec. Now that took a while because the early readings gave us a very different value, but over time, as we get more and more accurate measurements and put all the data together, the value started merging down to 73 kilometers per second per megaparsec, which is now one of the premier values for the Hubble constant. It may still change a little bit, but we're getting closer and closer to the exact value. Remember, once we know the Hubble constant, we can then look at any galaxy in the universe, measure its distance by measuring its recessional velocity, putting it on this curve, and then finding the distance to that galaxy. Just absolutely amazing. Something Hubble started over 100 years ago is now one of our premier tools to find distances to galaxies all over the universe, and also to find a very accurate measurement to the age of the galaxy by simply taking the inverse of the constant. 1 over age is the age of the universe in seconds. So it's absolutely amazing. So that's how we figured it out after 100 years of hard work, but we're not quite done yet. We're not done until we get even a better value for Hubble constant. So research will continue, experiments will continue until we get that thing nailed down as accurately as we can. Welcome to our lecture online, and here we're going to talk about something very strange. We discovered that the universe is expanding, and because of Hubble constant, we were able to figure out the rate of that expansion. But then when we continued to study the methods to verify the Hubble constant, and one of those methods was to study type 1a supernovas, and when we started looking at supernovas very far away with the Hubble Space Telescope, we began to realize something was strange, something was off, something didn't make any sense, and here let me explain. So here we have the Hubble constant, which is equal to the slope of this line, which is a relationship between the recessional velocities and the distance away for the galaxy. So for a particular galaxy that may be 30, 50, 80, 100 million light years away, we take a look at it, we determine the recessional velocity, we can then figure out the distance, we then we will see a type 1a supernova there, we measure the brightness of that supernova, and then we match the distance of that galaxy with the Hubble constant, and usually it's a dead match, not a problem. It is a nice confirmation that the Hubble constant is correct. But then when we look at galaxies that are farther away, we again use the recessional velocity to find the distance to the galaxy. And so, for example, this is where we think the galaxy is at distance-wise. And then we see a supernova explosion. We measure its brightness. We then figure out the distance to that galaxy using the type 1a supernova explosion. And guess what? The distance is actually farther away than we thought it was going to be using the Hubble constant. It actually came out to be farther away, which would indicate that the Hubble constant is actually changing in the far distant past. Remember, the farther we look in the universe, the farther back we look in time. So it looked like the Hubble constant wasn't constant all the way through, that it was actually declining. The Hubble constant was smaller, which means that the universe was expanding more slowly in the past and expanding more quickly today. So if we continue doing that, if we continue looking at galaxies further and further away, initially the distance that was determined by the Hubble constant matched the distance as determined by the supernova explosion. But then as we started looking farther and farther away, the supernova explosion seemed to have occurred further and further and further away than would be indicated by the Hubble constant, which means that the Hubble constant was decreasing in the past, or better yet, as time went forward, the Hubble constant was increasing as time went forward, meaning the acceleration of the universe the expansion of the universe is accelerating. Wow, that was really strange, because up until that time, and me personally as well, thought that the expansion of the universe was actually slowing down because of gravity. All the matter in the universe was pulling on each other, and it should slow down the expansion of the universe. Instead, we saw the opposite. The universe was actually expanding at a more rapid rate. See, the question always was, if the universe is slowing down, if the expansion is slowing down, will it eventually stop, and will the universe then begin to fall back in on itself and have like a big crunch instead of a big bang? But if this is true, and we believe it is, and it will continue that way, so the expansion will continue to accelerate, the universe will never stop accelerating and will go out forever and ever and ever, and never will come back together. Not that that makes a big difference for us, because that would be an event that's billions, if not trillions of years in the future anyway, but it's nice to understand the universe. It's nice to understand that this is what is happening, that the expansion is actually accelerating. And again, this was discovered by comparing the Hubble constant, which we found using Cepheid variables, and type 1a supernova that are close by, to looking at type 1a supernova that are far away. And all of a sudden, we realized that the Hubble constant isn't constant at all, but decreases farther back in time, which means the universe is expanding at an accelerating rate. That is quite amazing. So again, as you see, astronomy is a science that's continuously unraveling. We're continuously finding more and more of the evidence of what's happening in the universe. And as we find more evidence, things that we thought were true 10 years ago may not be true today. But we do know, by studying type 1a supernovas, that the universe is accelerating, is expanding at an accelerating rate.